ஓகேவா? ஹலோ. மைக் டெஸ்டிங், மைக் டெஸ்டிங். ஆ. ஹலோ, மைக் டெஸ்டிங். ஹலோ. ஹலோ. செக், செக், செக். 1, 2, 3, 4, 5, 6. ஹலோ, மைக் டெஸ்டிங். ஹலோ. செக், 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 செக். ஹலோ, மைக் டெஸ்டிங், மைக். ஹலோ, 3, 2, 1. 1, 2, 3, 4, 5, 6, 7, 8. ஹலோ, மைக் செக், செக், செக். ஹலோ, மைக் செக், செக், செக். மைக் டெஸ்டிங். ஓகேவா? ஹலோ, மைக் செக், 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 செக். எவ்வளோ வைக்கிறா? சரி. ஆ, 30 வச்சிட்டேன். ஹலோ, செக், 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 செக். 1, 2, 3, 4, 5, 6, 3, 2, 1. ஹலோ, 1, 2, 3, 4, 5, 6. ஹலோ, மை செக், செக், செக். மை டெஸ்டிங், மை டெஸ்டிங். ஹலோ, மை டெஸ்டிங். ஹலோ, செக், 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 செக். ஹலோ, மை டெஸ்டிங். ஹலோ, செக், 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 செக். This is working. Just testing, ma'am. Hello, check, check, check. Hello, check, check. My check, my check, my check. Hello, mic testing. வால்யூம் ரொம்ப கம்மியா இருக்கு. ஹலோ, செக், செக், செக். ஹலோ, 1, 2, 3, 4, 5, 6. ஹலோ, 3, 2, 1. ஹலோ, மை டெஸ்டிங், மை டெஸ்டிங். ஹலோ, செக், செக். ஹலோ, செக், செக், செக். அது இன்க்ரீஸ் பண்ணவா? ஆ. ஹலோ, செக், 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 செக். ஹலோ, செக், செக், செக். 1, 2, 3, 4, 5, 6. ஹலோ, மை செக், மை செக், மை டெஸ்டிங், மை டெஸ்டிங். ஹலோ, மைக் டெஸ்டிங். ஓகேவா? காலர் மைக்.
It is okay. Good morning, everyone. Welcome to IMSC. So we are just starting today. So we'll start about remembering Professor Rajashekharan, who I think I don't want to say anything because we'll all learn, but I'm really missing him. And first, I'm handing over to our director, Professor Ravindran, who was part of organizing committee also, to say a few things.
Okay, so thanks, Winstry. So let me welcome all of you to our institute, IMSC. And I always take this opportunity to actually say a few words about IMSC because there are people who are the first comers, to this institute. So IMSC, as you all know, it's a premier institute doing research in 4 different areas: theoretical physics, theoretical computer science, mathematics, and computational biology. We have quite a lot of faculty members, about 50 faculty members at present, and about 120 students. Very vibrant institute, as you will see, in next 3 days. We have very good library, and also computational facilities. And I'm happy that you are all here. I think it's after COVID, we have this big meeting in ionology physics. There are many meetings that are going on for last 3 years after COVID. And this meeting is very special for IMSC because actually this is to honor one of our beloved colleague. For me, he was a teacher, and later happened to be in the same corridor where he used to sit. So it is about honoring Professor Rajashekharan, fondly called Rajaji. And I joined this institute in sometime in 80s, I think, end of 80s, and he was the joint director. And he looked exactly same when he passed away, very look-wise, and also as a personality, as a mentor, as a visionary, as a scientist, okay, and also a person who guides everybody. He was like a fatherly figure to most of us, and particularly to me. And I'm really happy that I'm part of this team to sort of have a 3-day program to honor, because he always liked physics. And like Manjari said, we have been missing him a lot. Okay, thank you. I have to chair, okay. So I think, I said quite a lot about Rajaji, and you will hear more from Professor Murthy, who had a long association with him, more than I did actually. So I will request Professor Murthy to actually talk about him. I don't think you need an introduction to Murthy. Murthy was our former professor at IMSC, particle physicist, as you all know. And he had also had a long association with him. So I think I'll stop here and request him to.
Okay. Thank you very much. And it's a pleasure to come back and, meet all the old friends, and especially Neeta and Rahul, who are not in Chennai anymore, and they are. Okay. So this is a tribute to Professor G. Rajshekaran, whom we fondly called as Rajaji. So I will refer to him as Rajaji throughout. And the title of the talk is taken from the title of his autobiography, which is My Inward Bound Journey. I'll give a reference to that autobiography later. Even though my bias may show in this talk, much of what I am going to say is taken from the autobiography itself, some of them in his own words. So, and of course, I sent it to some of his old friends like Divakaran, Mani, and others who also commented on this and gave me some information about Rajaji, which I have included. So let me continue. So this is the outline of the talk. It's more like a biography of Rajaji, a scientific biography of Rajaji and his achievements. So growing up, then his scientific contributions, there it will be a selection because it's huge. And then I'll talk about rebuilding IMSC. We are sitting in this hall and we should know what all he did for this institute. It's enormous. I mean, especially the young people, young IMSC people should know that. And then back to research, and he worked on the India-based Neutrino Observatory project and his contribution to teaching and outreach. This is how I have organized it. And his early years, he was born in 1936 in a very small town called Kamudi in the Ramnad district. Now it's called Ramanathapuram district in Madras Presidency. He's the eldest of 5 brothers and 4 sisters. And his father owned what we call as Patrakadai, which is a shop selling vessels. And he went to school in those days, primary school, middle school, and high school, all in Kamudi. And after 10th, next 2 years were spent in American college, and that was called as intermediate in those days. Now it is 11th and 12th, plus 2, as you call it. And when he was in American college, he came to use the telescope that was in the college. And he gushes about the first view of the moon that he saw through the telescope. And that kind of initiated his deep interest in physics. And then he went to do the BSc Honors in Physics at Madras Christian College. While he was at Christian College, there was this Professor Tangaraj who had research projects with people in TIFR. Professor Bernard Peters, who in the 50s was in Tata Institute of Fundamental Research, M.G.K. Menon. All these people used to come to Madras Christian College and do these cosmic ray experiments, sending balloons. And they needed a lot of students to help in this because the balloon would go up to a certain altitude. After some time, it would die down. So they have to fetch the instruments back. And all these college students were helping them in these experiments. So Rajaji came in contact with these people. And not only they came here to do experiments, they used to give talks in the college. So that kind of was an inspiration for Rajaji. And then he went to join the Atomic Energy Establishment Training School. It was not BARC at that time. It used to be called Atomic Energy Establishment Training School. And this was in 1957. He went to join this Atomic Energy Establishment. In the first batch, there were about 150 trainees, engineers, chemistry, physics, and I think that's probably what they had in the first batch. And then after completing the training, 1 year training in the training school, he joined TIFR, and he was first among the 150 trainees in the first batch by a distance. In fact, he got the gold medal on the 50th anniversary of the training school in 2008 from Prime Minister Manmohan Singh at that time for standing first in the first training school. And since they had a choice, or he had a choice, he joined TIFR in 1958. And up to 61, he was in TIFR. He started working on hypernuclear physics, which was one of the fields at that time which was at the forefront. And B.M. Udgankar was one of the people who was involved in that. And then he started working on this. And then he also got interested in digging deep into quantum field theory. He learned quantum field theory from S.N. Biswas, many of you may have heard about him, and L.K. Pandit, who had just joined Tata Institute of Fundamental Research at that time. So at this time, Rajaji had started supporting his family because his father had actually taken a lot of loans for his education. And when he was in TIFR, he was supporting, and he ensured that the support would continue even when he went to Chicago for his PhD. So here is the photograph. This is a very famous, I consider it as a very important photograph because it contains so many people that we know who later contributed to development of physics and science in various other places, including popularization of science, like MP Parameswaran, who is in this, I think this is MP Parameswaran. He is the one who started this Kerala Shastra Sahitya Parishad. And it also has, apart from Rajaji, my other collaborators, C.V.K. Baba, who is here, and K.V.L. Sharma, who was one of my advisors too in my thesis work. So there are many illustrious names in this, and this is a photograph which one should keep. It's good for any archive. And he joined TIFR after the training school. It was a norm in TIFR those days that after spending some time in TIFR, they would go and do their PhD. They were encouraged to do their PhD in some very good places. And at that time, Rajaji in 1961 attended the TIFR summer school in Bangalore, where the lecturers were Gelman and Dalitz. And this was actually the summer school in which Gelman for the first time talked about SU3. Though he did not introduce the quarks at that time, he talked about the eightfold way and the octet baryons and the decuplet baryons in that meeting. And in fact, Rajaji mentions that Dalitz kept asking him the question, what about the fundamental representation of SU3? Where is it? So, but one had to wait for 2 more years to see that fundamental representation appear in terms of the quarks. So after encouraged by Dalits, whom he had met in this TIFR summer school in 1961, Rajaji went to Chicago. And it took 3 months on the ship to go to Chicago. So he studied and prepared for the Chicago basic exam. It was a dreaded exam, apparently. And by the time he reached, he was already ready to take the exam. So within 2 or 3 months after going to Chicago, he took this Chicago basic exam and he topped the exam. And I heard from Divakaran that stock of many Indian students went up because of Rajaji's performance in this Chicago basic exam. And he did something else along with doing research with the Dalits. I'll come to that in a little while. A.K. Ramanujan, I don't know how many of you heard of his name. A.K. Ramanujan is one of those people who was actually one of the founders of the South Asian School in Chicago. And he was the translator and interpreter of many Tamil and Kannada epics. He translated Kannada epics into Speaking of Shiva, and then Tamil Sangam literature like Silapadikaram and Manimekalai were translated by him. But since he grew up in Mysore, his Tamil was not great, and it was Rajaji who helped him. Rajaji's knowledge of Tamil language and literature was very good, and it was he who helped A.K. Ramanujan in translating and interpreting this Sangam literature. And I think this was the very first time when the Sangam literature was brought into English in full. So this is about Rajaji's education and his growing up. So coming to his contributions, scientific and also otherwise, Rajaji is like a big banyan tree, you know. So many branches are there, so many things he did. And for example, he wrote research-wise, there are more than 200 papers, more than 20 reviews. He contributed to rebuilding of IMSC and teaching at every level, science outreach in English and Tamil, mentoring young scientists, contributions to other institutes, and to the development of underground science laboratory, which is still in works. And all this was done, you know, from his journey, starting from Kamudi, Madurai, Madras, Bombay, Chicago, Oxford, again Bombay, Madras, and Keck in Japan. And I have left out many other places that he went to, but these were the places where he spent at least more than a year. So it's hard to cover these things in the next 30 or 40 minutes. So I have to make a selection, and that is necessarily biased. So in his thesis work, which was done in Chicago first, and then last 1 year was spent at Oxford, he worked on what are called as the shadow poles. So after the SU3 model of Gelman came, Yang had a serious objection saying that it has to be wrong. Because one, for example, if you look at the SU3 octet or decuplet, they are not degenerate. Now, they appear as poles on different Riemann sheets in the S matrix language. And obviously, in the symmetry limit, they have to collapse into a single pole, and that did not happen. So Yang and Oakes commented that this has to be wrong. And this problem was solved by Rajaji and, of course, with Dalits, where he showed that there can be a retinue of poles, even in the symmetry limit, and these are called as the shadow poles. And that solved this problem and removed the objection to the very basic objection to the SU3 of Gelman. So this was a formulation which also kind of led to the reformulation of the basic tenet of S matrix theory. So Rajaji completed his thesis in just under 3 years. After spending a year in Oxford, because Dalits, who was on sabbatical in Chicago, went back to Oxford, and Rajaji also moved to Oxford with him. And he returned to TIFR in 1964, just after submitting his thesis. So he had not completed his defense, and his defense was actually conducted by post. So today, even we do, online, many people try to object. but those days it was done by post. The committee was headed by Telegdi, and he was sent questions by post, and Rajaji answered the questions by return post, and then he was awarded his PhD by University of Chicago. Then the next work that he did, which he started doing while he was in Oxford and completed after coming to TIFR, is a very interesting work, and it's also a bit audacious. And this is a work which I like very much, because it's still an open problem, and it looks like the solution given by Rajaji and Dalitz at that time is actually the correct solution. So the problem is the following, that if you look at the nucleon and its excitations in the hadron, in the baryon spectrum, okay, so you will see that the ground state is, of course, the neutron and the proton, as we know, at 940, and the first odd parity excitation is a half minus state at 1535 or 1.5 GeV, slightly above that. And there are two problems here. In the SU3 limit, of course, nucleon and lambda, they are all in the same octet. But if you look at the first excitation of lambda, which is half minus, similar to 1535 here, this is at 1405, and this difference is only 300 MeV as opposed to 600 MeV excitation energy. And this is actually, odd parity has to be the first excitation. The ground state is even. Two problems. There is a Roper resonance, which is an even parity excitation. And if it's a radial excitation of the nucleon ground state, then it has to be much higher than here, about almost around 1000 GeV above the nucleon. And in fact, instead of first odd parity state coming before the radial excitation comes before that. This is an open problem in QCD, where Roper resonance has not been fully explained. And there are many solutions to that, and have been proposed, but none of which is concerned. So these are the two main problems. And Rajaji actually proposed that this lambda 1405 is not a 3-quark state at all. It has to be a molecular hadron. Only then it can come so low. There may be an admixture of the quark state, but what makes it come down is the molecular state. That it's actually a bound state of k bar n, and it is not a pure 3-quark state. So this, in the 60s, it is an audacious suggestion that this is a molecular hadron. And now, of course, people are thinking that Roper resonance may also be a molecular hadron, or probably a highly deformed state like in nuclei, which comes down due to the deformation. So now in last few years, there is a growing evidence from lattice QCD calculations that this is indeed a baryon molecule or a hadron molecule. So what Rajaji did in the 60s is now coming back, and the solution proposed is coming into prominence. In fact, this is in the physics news. I think this was in 2017 or 18. In the 1960s, the Australian physicists Richard Dalitz and colleagues, actually it should be Rajaji and colleagues, because Rajaji was the first one to propose, and then they wrote the paper together. In fact, Rajaji presented the proposal in High Energy Physics Conference at Aligarh AMU, Aligarh University. So so the statement here is Richard Dalitz and colleagues suggested that lambda 1405 could comprise of an anti-kaon meson bound to nucleon. So these calculations now today, they are increasingly getting accepted. In fact, there is a magnetic moment calculation which shows that the strange quark does not contribute to the magnetic moment of lambda 1405. And that is possible because it is bound inside k bar, and that's a pseudoscalar. So therefore, it does not contribute to it cannot explicitly contribute to the magnetic moment. And this, in fact, it's interesting that this work was done by Derek Lineweber et al., whom we knew as a student from McMaster University. Even Rajaji knew him. So he's now a professor at Adelaide. So next, Rajaji's interest shifted to, after coming to TIFR, after the paper by Weinberg and Salam, he shifted interest into gauge theories. He was an early proponent of the gauge theories. His lectures delivered at Saha Institute in 1971 and also in some other places was the first coherent account of the Yang-Mills fields and the Salam-Weinberg electroweak theory. And this is unpublished. It's a TIFR report. And this is well before this electroweak unification became a paradigm for high energy physics. So his lectures were attended by quite a few people, and the notes even contained his conjecture that massless Yang-Mills gauge quantum cannot exist freely because of the infrared divergence. This was, one should remember, this was in 1971 when QCD was not yet there. And here is a statement by Pakwasa, who attended these lectures. He said, I got hold of his lectures on Yang-Mills theory given at Saha Institute. No, he didn't attend. He got hold of the lecture notes. And he says that became his Bible. I still have my marked up copy, dog-eared copy, and this contains prescient remarks about confinement and other ideas. And similar sentiments were also expressed by Lalit Sahgal, who actually attended these lectures. Perhaps Rajaji's best work in this connection, even though he didn't publish anything, he didn't to the development of gauge theory, was that the very first calculation which showed the finite contribution at non-leading order after Etouff's general theory, it was, I think, the first paper which showed the finite non-tree level computation in the standard model in the case of muon decay. This was not the one which was published first, but I think that was one of the earliest calculations to be done in using the standard model or electroweak model at that time. So the electroweak gauge theory was not taken seriously until the discovery of the neutral current in 1973. So all of Rajaji's earlier work was before the discovery of neutral current. Now, after the discovery of neutral current, I don't know how many of you remember that the interest in Weinberg-Salam theory just went up. It shot up. I mean, because that was one of the predictions of Weinberg's paper. In fact, when they saw the neutral current event first, they called it as the Weinberg event. Okay. So immediately then Rajaji combined with KVL Sharma, and they wrote the first model independent analysis of the deep inelastic neutrino scattering data. And the equations that they developed for getting the limits, etc., were called as master equations by Sakurai, who further developed further built up on what Rajaji and KVL Sharma did. Series of papers were followed, both by Rajaji and KVL and also Sakurai and others, which ultimately led to the complete determination of the neutral current coupling constants in isoscalar and the isovector sectors. And in fact, this was necessary to establish Weinberg-Salam model as the template for the standard model later. So 70s decade was a very productive one. Rajaji et al. Worked on the phenomenology of electroweak model, which became the standard model later with the addition of QCD. There is one regret that Rajaji expresses here, that he could not contribute substantially to the early development of electroweak gauge theory. He says that although I missed being on the stage, I sat on the front row. There was no bitterness in this statement. And later on, he did contribute substantially to the development of the standard model. He never said it as an excuse, but I found out that by talking to other people, Rajaji's father was very ill at this time, and so he had to go up and down and travel a lot to take care of his family matters also. So might have, but this was never given as an excuse by him or even mentioned. So in 1974, Rajaji thought that after all this hard work, he will take a holiday and go to Hawaii. And he was invited by Sandeep Pakwasa to visit Hawaii for a few months. So in fact, Rajaji wanted to combine it with a holiday, so he took the whole family to Hawaii. But a day or two after landing in Hawaii, suddenly comes this announcement of narrow resonance in E plus E minus collisions at 3.1 GeV. This is the JPSI, which created a lot of excitement at that stage, at that time. And for the next few days, he didn't have any peace. He, Pakwasa, and Tuan sat and worked out all possibilities, whatever possible explanations of this bump. Something like 10 explanations were worked out for this 3.1 GeV bump, one of which was actually the correct one. So they exhausted all the things, including the correct one. And it was one of the earliest of many similar papers. It contained an exhaustive list of interpretations, including the correct one, as Rajaji says. In 1976, Rajaji moved to Theoretical Physics Department of Madras University, which was one of the finest departments at that time, headed by P.M. Matthews. And in fact, TRG is here. He was there in that department when Rajaji joined. And along with Matthews, Sitaraman, and Bhamati, Rajaji also joined this department, which really flourished with the addition of all these people. I'm not too familiar with the work done in Madras University because it related to, at that time, what was a distinct possibility, that is the integer quark model. So they spent a lot of time, especially with Rindani, who had joined as faculty in 1978. They did a lot of work on how to observationally distinguish the fractionally charged quarks and integer charged quarks through experiments. There are more than 20 papers. Just to summarize what he did in Madras University in those years, for example, there is this equivalence of Parisi model with confinement in QCD. Rajaji considered this as a very nice paper. This was done with V. Srinivasan and later with M.S. Sriram. And then the remarkable properties, here he moves to integer charge quark models. It begins with the paper by Prabir Roy and Rajaji. Remarkable properties of both broken color QCD with integrally charged quarks. Then they went on to devise many tests using in these jet experiments. And this was done with two of his students, Jayaraman and Lakshmi Bala, who have distinguished themselves in various other places already. And then the discovery, this is an important paper, discovery of new effects invalidating the time-ordered equivalent photon method for the production of charged particles of spin greater than half. This is one of the things which was stated almost like a theorem, this equivalent photon method. Whenever you have electron interaction, the virtual photon can be replaced by a real photon, and you can, where it's forward scattering. There it's almost close to be on mass shell. And so you can replace it by as though it is the photon that is initiating the interaction. This is the equivalent photon method. So they showed that this is valid only for massless spin 1 particles, and it's not valid when the spin 1 particle is massive. I think that was an important thing. So his collaborators, I mentioned the names of all the collaborators during this period. I think Srinivasan, Rindani were his colleagues. Lakshmi Bala and Jayaraman were his students. M.S. Sriram, Jatindra Bajaj were on his project. He had a big UGC project at that time, and they worked with him on the project. And later, M.S. Sriram joined as faculty. So coming to Mat Science, he moved to IMSC in 1984. And his focus shifted to neutrino physics. I remember when I joined, Joshipura had joined just before me. He called both of us to his office. And then he just put Bethes paper in front of us and then said that, look, this is the Bethes solution for solar neutrino problem. So it's a beautiful paper. You read it. And then this is still a toy model because it is done for 2 generations. See if you can do it for 3 generations. So that is how my collaboration with Rajaji and Joshipura began at that time. And then we continued that collaboration after Mohan Narayan joined me as student and Uma Shankar was my colleague. So together we, after the discovery of neutrino oscillations, we were one of the first to do a comprehensive realistic 3-generation analysis of solar and atmospheric neutrino data to pin down the range of parameters. So we at that time we got both large angle and the small angle solution. The region for small angle was actually getting narrower and narrower, and it was a small angle solution that large angle solution for theta 2,3 that survived from that time. But the elements of the correct solutions were already there in our analysis at that time. Now, having started this full 3-generation realistic analysis, we also extended it to supernova neutrino emission along with Gautam Datta, Indumati, and myself. And this, in between with Rahul Sinha and Balaji, he also did this analysis of day-night effect with solar neutrinos. At that time, it was still an open question, and they showed that there is not much difference. And they also looked at this very interesting eclipse effect. So all this was done in the realistic 3-generation framework. And in a corollary of that is this very important and notable contribution at that time. When the choose reactor neutrino analysis, neutrino data came, their initial analysis was using the 2 generations. And obviously, if you use 2-generation analysis for choose data at a smaller distance, you don't find any result. It was a null result. So that analysis was completely wrong. And Mohan Narayan and Rajaji and Uma Shankar did the full 3-generation analysis where the choose data actually put a limit on the theta 1,3 angle. At that time, theta 1,3 was not known. Nobody had an idea of what its value should be. And this was the first determination of the theta 1,3 angle. And they showed that this third mixing angle has to be less than 12 degrees using the choose data. And they wrote to the experimentalists saying that you have a beautiful result and your analysis is wrong. So immediately the choose people changed their paper, did the full analysis with 3 generations. And then that paper, that's the first one in which we have any idea of what theta 1,3 should be. It's a limit, it's not a determination of the angle, and the limit was 12 degrees. When the paper was published, even after revision on the archive and later when it was published, there was no mention of this information which was conveyed to them. And I mean, it's very clear that immediately after this conveyed, their preprint changed, and then the published version changed. There's absolutely no acknowledgement of the contribution from Mohan Narayan, Uma Shankar, and Rajaji. This keeps happening. One should be very aware of these things. And now we have confirmed this analysis, this by actual determination of this angle from Diabe and Reno. This is about 9 degrees, well within this limit. Okay. Here are all the collaborators from this period in the 90s. And later on, Rajaji constructed the mass model with F4 symmetry. Actually, it became a very well-known paper. This he did with Ma. They actually constructed a mass model which which gave a neutrino mass matrix based on a symmetry, which is the A4 symmetry. And he also looked at how to generate neutrino masses. And a new mechanism was arrived at, but in which Higgs will become a composite. And this was done with P.P. Divakaran. And he also looked at the evolution of neutrino parameters from the unification scale down. So because you have a mixing matrix for the neutrinos and you have a mixing matrix for the quarks, and they are very different. Why are they so different? So if you assume that they are very similar at the unification scale, then you can do the RG evolution backwards and show actually that the neutrino mixing angles can be what they are in principle. So this work was done with Farida, Arun Mahapatra, Sanjeev Agarwala, and there are many other collaborators. This he almost continued till 2 years ago. He was still working on such problems. So in the 60s and 70s, there were many anomalous events that were observed in Kolar goldfields, and these were called as Kolar events. These are events in which the event took place in the air, and then if you gave 2 prongs or 3 prongs in the proportional detector, so by working backwards, you could identify the vortex in the air. Now, at 2.7 kilometers underground, neutrino interactions in air cannot give you 8 events in about 20 years of running. So this was a puzzle, and these were called anomalous Kolar events. They have not been withdrawn, so they must be there. And these events were reinterpreted as possibly due to dark matter, because there are only 2 possibilities at that depth of 2.7 kilometers, either neutrinos or dark matter. So an interpretation was arrived at saying that this is due to the decay of dark matter. There are a lot of problems with this interpretation also, but nevertheless, that conundrum is there. I mean, what else can it be? So, and proposed an experiment at INO to confront this hypothesis with Datar, Indumati, myself, and Satyanarayan. There are still many problems with this interpretation, but it just shows the kind of adventurism that one has. So there are other contributions which I am not very familiar. Rajaji and A.K. Mishra discovered new forms of quantum statistics, such as ortho, null statistics, etc. Their theory of generalized Fock spaces enlarged the framework within which familiar quantum field theory and statistical mechanics reside. And then he also looked at Aharonov-Bohm effect in Kaluza-Klein theories, extended to include Berry phase, etc., with R. Parthasarathi and R. Vasudevan, and consequences of non-commutative standard model for physical processes with many other collaborators. I'm not too familiar with these things. How much more time I have? 10 minutes, okay. So now I'll come to moving away from his research, come to his contribution to rebuilding of IMSC. Professor Alladi Ramakrishnan was founder director of IMSC. He retired in 1983, and IMSC was looking for a new director. A committee consisting of Vice Chancellor of Anna University, Kulundeswamy, B.M. Udgaonkar, and M.S. Narasimhan actually proposed Rajaji as the director after Alladi Ramakrishnan. Unfortunately, a change came about, and Rajaji was requested by Ramanna to take charge as joint director and not as director, and not as deputy director. And his letter of appointment clearly says that during the director's absence, the joint director shall have the full powers of the director. Rajaji was initially reluctant, and then he agreed, and along with Professor Seshadri went about rebuilding IMSC. So here are various things that he did, which are very important for later development of IMSC. One, of course, we didn't have the land across where many of you are staying in the guest house. So he worked with, with the help of Kulundeswamy, who was the Vice Chancellor of Anna University, and using his contacts with Ranganayakam at that time, Education Minister, he got the land for our hostel and the guest house facilities within about 3 to 4 months' time. That was quite remarkable at that time that he could get that. And then we started building the hostel and the guest house at that time. Still a smaller facility, not like today. And then second important thing, this happened just before I joined the institute in 1986, is the shift to the central government salary structure, because by that time the institute was almost fully funded by the Department of Atomic Energy. So he convinced DAE that all DAE institutes should shift to the same central government salary structure and service benefits for the faculty and also the administrative members. This had actually much larger effect than just IMSC, because immediately IOP also got the same thing. And then when HRI started, from the beginning, they had uniform central government scales, which is very similar to all other institutes under DAE. And with that, one could attract talents. And within about 4 years, from 84 to 88, the faculty strength, which was about 12 in 1983 when Alladi Ramakrishnan retired, went up to 31, attracting many brilliant young minds in mathematics and theoretical physics from all across the country and abroad. And he also laid the foundation for graduate school at IMSC. In fact, we were all involved in that effort. When I say Rajaji's contribution, he was the leading member of all these things. There were many other people who were involved also. And this graduate school started at around that time. And for the first time, this MSc by research was also started. And at that time, I think we were the first ones to get it, to start an MSc by research program. And no university was prepared to give this MSc by research degree. So, in fact, Rajaji was made a member of this Senate of Anna University so that he could propose this, and Kulendra Swami, who was the Vice Chancellor, also supported it. And that's how the MSc in research started. Then starting of theoretical computer science research program with very young faculty members. That was quite a daring move at that time. And this in 2001, Rajaji retired formally from IMSc, but continued to work as emeritus professor till the end. Till last year when he passed away, he was there. And most of this period was consumed by his effort in creating a world-class underground laboratory. This is still a work in progress. So many Rajaji's friends and others came to attend this festival, where we discussed in great detail and produced a report on construction of a deep underground national laboratory. So this here, we have to remember that India was a pioneer in neutrino experiments. One of the very first underground laboratories in the world was at KGF. And it was also the deepest as long as it was operational. The very first observation of the atmospheric neutrino event in 1965 was observed in KGF. In fact, here I would like to point out that Nobel Prize has been given to the observation of neutrinos from the sun, supernova, reactor, and the laboratory neutrinos. What is missing is the atmospheric neutrinos. This is a bit strange, and I think it was a pioneering effect which should have been recognized. I mean, I don't know, it's not recognized, that's all. Not recognized at that level. So Rajaji got involved in this from the very beginning, along with many others. But it was during his lifetime, it didn't come about. There was a lot of problems. So the initial support, which was great actually, from the Tamil Nadu government before 2012, turned to apathy by 2015. And finally, the support evaporated in 2020 after more than 2 decades of work from nearly 100 scientists, engineers, students, and even many officials who supported the project at both state government and the central government level. Rajaji was involved in every one of the activities of this underground laboratory project. In fact, you can see in these photographs, he's walking through all these fields, going up and down the streams and the mountains there at the site. Okay, 5 minutes. I think I'm more or less there. So contribution to other institutes, this is of course very well known that while working in Madras University, he was the head of the department from 77 to 80. He was in charge of the physics group and the physics teaching at Chennai Mathematical Institute when they started the physics program in 2002. Served on governing councils of national institutions, syndicates of universities, and also review boards of many universities. He was there. Served on many committees of science academies and committees of DAE, DST, and UGC, and various other institutes. He has been honored. He is a fellow of all the 3 academies, recipient of Meghnad Saha Award and SN Bose Medal of INSA. And teaching and public outreach was always there for Rajaji. Apart from regular teaching at TIFR and Madras University, IMSC and CMI, Rajaji was involved in very multifold activities, running and teaching in most successful DST, SCRC schools in theoretical high energy physics. This was started with Mukunda, then continued with Rajaji, and initiated physics teaching for talented students, which is still going on. And the Sunday classes in Madras University, with the help which was started with M.V. Satyanarayana, who just passed away a few months back, of Pondicherry University, it completed 25 years. Every Sunday, Rajaji, when he was in Chennai, he would go there and spend 3 hours teaching the students. And the students came from all over southern Andhra Pradesh, southern Tamil Nadu, and of course, Chennai. So then conducting refresher courses for which Indu, me, Rajaji, we have gone as a team to so many places in TN, Kerala and Karnataka. And this was supported by the Academy of Sciences. And then public outreach for INO. Here we have gone from research institutes to officers of the state government, to tea stalls in the villages. If somebody says that we didn't do outreach correctly, I think they don't know what all we have done. So, and Rajaji was there, in fact, especially while speaking to villagers in tea shops, etc. He could speak Tamil fluently, and that was of great help. And we have gone through many places in various states for this public outreach. Then he started writing in Tamil because he wanted to reach a larger audience. He started writing. First, he started writing about neutrinos, then extended it to all of science, and then wrote many articles in Tamil every month to the Tamil magazine. It was edited by Dr. Jayaprakasam, and all the articles are now collected as in the book form. So he was an eternal optimist. For example, Rajaji, he believed that the underground lab project will be built. He said it will be built. We will keep working. And that was, in fact, one of our great motivations to continue to do it. Apart from directly working on site surveys, I don't know, he involved himself in every possible activity regarding that, including, of course, doing the physics goals for ICAL with Indumati, Neeta, and myself. And he also attended every meeting, every collaboration meeting, not just of ICAL collaboration, of this NDBD collaboration, dark matter collaboration, and participated in every one of the futuristic laser plasma accelerator discussions. He brought many people to collaborate with Indian groups, was extremely keen on universities participating, even taking lead in many projects. More importantly, wanted mega projects in science to take off, especially in remote areas, to inspire students locally to take science and contribute to growth of science and technology within the country. So he has been an inspiring leading member of physics community in India, lived an honest, candid, and simple life in science and in everything. This is his family, his 2 daughters, grandchildren, and his wife, Sadantra, who is sitting next to him. So I think I'll stop here. The sources I said I'll give. This is available. Rajaji's autobiography is in Google Books. Anybody can download it and read it. And then there is a Rajaji Fest Proceedings, which is available as an IMSC report. This was edited by Indu Parthasarathi. And you can also go to his memorial website if you want to add anecdotes, your own stories, or you want to add pictures, please do so. So thank you very much for listening.
Thank you, Professor Murthy, and you really brought Rajaji to this auditorium. You have some questions?
In the book on dispersion relations by Barton, around 1965 or so, there's a reference to the paper of Rajsekharan and Dalits. And it gave a a reference and volume number and phys letter. And so I was curious to see the paper, but when I went there, it wasn't there. So it was actually not a phys letter, but a physics letter.
Physics letters.
Yeah.
paper, yeah.
So even a textbook can have a
That's
mistake
it.
of this kind.
Yeah, yeah.
But the point is, it was only a couple of years after the paper, it was already cited in a major textbook.
Yeah, yeah. In fact, Dalitz mentions that he met Yang in 1990, some meeting in the 90s. And Yang, in fact, mentions to Dalitz that we never understood what was wrong with our paper until we read your paper, on shadow poles.
Okay, so any other questions, comments? Anyway, we'll have a separate session for that. Then that.
Thank you very
Let
much.
me thank Mr. Murthy for this wonderful reminiscence of. Okay. So I'll move on to the next talk by Adarsh Singh. It's going to talk about our fractals behind flavor mixing of the standard model.
Okay. So firstly, thanks to the organizer for giving the opportunity to present our work on this occasion. So in this work, flavors from fractals, what we are trying to do is we're taking two different concepts of flavors from particle physics and the concept of fractals, which is a nonlinear concept from classical phenomena. So we're trying to get some insights about the flavor physics in particle physics from the fractals. So to give a brief introduction about flavors, now in standard model, it is known that the different types of fermions which are there, they are found in 3 copies. So one of these is lighter, one is heavy, and the third one is even heavier. Now this trend is observed for both leptons and quarks, and they have same quantum charges under gauge groups, but they differ from each other in their masses. So their mass scales are different. Now further, the mixings of these fermions, it's also not uniform. It varies. So for the neutrinos, the mixing is much more. For the CKM or the quarks, the mixing is moderate, and for the charged leptons, there is a small mixing. So in some sense, from these simple, you can say the gauge charges, we are getting some complex Yukawa, we can say Yukawa parameters, which are accounting for the masses and mixes by some phenomena. Now people have tried to account for different masses, how you can produce the different mass scales to move away from the Higgs web scale. So the famous neutrino mass see some mechanism works on that you consider some high energy or more massive field and couple it by the standard model field, and then you will get sufficient small enough scale. Now people have tried various other mechanisms such as radiative correction model, and then there are linear chain masses model, or there are extra dimension model where they localize the wave function on different sites to produce different mass scales. Now more than that, there are also models to explain why there are only 3 copies, and there can be more than 3 copies, 2 copies, 4 copies or something. So people have also tried to come up with some models, which are these string extra dimension models, where they consider some kind of T-branes and then they intersect each other and produce these 3 numbers. Similarly, there are mechanisms to explain the intergenerational mixings too. So the overall motivation is that there is something physics, some underlying physics, fundamental physics, which is going on at some higher energy scale or small length scale, which when we look at in the standard model, what we're getting is the effective physics. So such as an example is shown in this slide. It shows the linear chain mass model. So there are these extra high energy physics fields which are coupled to each other in a certain way. And when you integrate out these heavier modes, what you get at the small scale is a coupling y effective, which is not really the fundamental parameter. It is the effective parameter that you get once you integrate out these fields. So the motivation is that there is some underlying fundamental mechanism going on, which at lower energy scale gives us the standard model. Now, so moving along that motivation, we wanted to use fractals because of some of the properties of fractal which are unique to them, such as they are self-similar. That is, if you take a fractal and then you zoom on the fractal, then after a while you get the same structure. So in a sense that even if you change the scale, you get the same properties for the fractals. So this can be vaguely related with the fact that we have these three copies which have the same properties, but they were at different mass scales. Now, furthermore, the fractals have non-integer dimensions or fractional dimensions, which is very unique to them. And even though being very complex, they can be generated naturally with the simple transformations. So you start with a some simple structure, and then you consider again a simple transformation on that structure, and then you apply the process iteratively. So as the iteration goes on, you get more and more complex structure. So more often, fractals are produced by recursive process, so they can exist in nature. And they have been found in nature in various places, such as coastlines, snowflakes, the cloud formations, uh, the tree branches, etc. So people have, because of this iterative process and this non-integer dimension, people have used this fractal in further theoretical sciences, in computer science, biology, and recently in quantum computing too. Now, it's not that fractals have not been used in the context of high energy physics. So there is a paper by Professor Hill. His paper is around, it came around 2002, where he tried to use the fractals to produce extra dimensions which are fractional. They don't have integer space-time dimension, but they are fractional. So here, what we are doing is a bit different. We are not trying to account for extra dimension. What we are doing is we're trying to use these complex structures since they have good connectivity. So they might account for intergenerational mixing. So that was the one of the motivation more, that maybe they can also account for generational mixing apart from that different mass scales. So the idea that we are implementing in this project is we are taking the case as an example case, the Sierpinski triangle. So this is the triangle that is formed after two iterations, the second one. So it has 15 nodes. So the number of node of the current graph you can find by 3 times the number of node of the previous graph minus 3. So you start with 3, 3 times 3 minus 3, next is 6, 6 times 3 minus 3, this will be 15. So that way, we thought of working with this structure. It looks sufficiently complex and it has good connectivity. So this is our example case. Now, what do you mean by node? We are implementing this in the context of deconstruction formalism. So we will apply it in the theory space. So when you have two nodes connected, so at each node, in the context of fermions, we have left and right fermions. So when two nodes are connected, let's say node I and node J, that means the fermions of Li and Rj are connected, and also Ri and Lj. They are connected to each other by some coupling strength. So we can get this picture, and the corresponding Lagrangian, we can write it as this. Now there are some formalism such as this clockwork formalism, which also works on these theory space models, but it's a linear chain model. It does not have this 2D fractal structure, it's just a linear chain. So, but the clockwork has this left-right asymmetry. So it has n number of left-handed fields and n plus 1 number of right-handed fields. Here we are putting them on same ground. So we have 15 left and 15 right here. Now, since clockwork has this asymmetry in left and right, so what happens is when you write the mass matrix, you get the rectangular mass matrix. So from linear algebra, there is a result that says that if you have a rectangular mass matrix of n by m dimension and your m is greater than n, then you will have at least m minus n0 modes. So clockwork models, they guarantee at least 1 0 mode because they have n and n plus 1. So the difference is 1. Now once you have a 0 mode, the other thing is to produce the smaller mass scales, you need to localize the 0 mode. Once you have 0 mode localized, then you can couple the Higgs with the standard model and get the sufficient whatever mass scales you require. So clockwork has that freedom that doesn't matter what kind of matrix you take, whatever element you take, it will have the 0 mode. The only constraint you need to take into account is the fact that that 0 mode has to be localized. So in this paper that mentioned here, we have looked at some of the explorations, what we can do, changes we can do, but still retaining the localization property. Now, with this structure, this fractal structure that we have considered here, we don't have that privilege. Since we have 15 left and right fields, there is no asymmetry in them. So mass matrix will be square matrix. So in general, there's no need to be any 0 mode. But with this structure, there were 3 0 modes. Now the fact that there was 3 0 modes, we can relate it with the fact that in the standard model, we have 3 copies, that is 3 generations. So in a sense, it is naturally explaining why we have 3 flavors in the standard model. Now the other thing is that those 0 modes, once they are produced, they need to be localized. Now if you consider any graph randomly, the modes, they might not be localized. More often, they will not be localized. And same was the case here. It was not localized, just as in clockwork. So what we do is, for that, when two nodes are connected, node I and node J, then there is this coupling parameters Qs, which are connecting two nodes. Now what we can do is, another linear algebra result we can use, which says that when you have a matrix A, which has some n number of zero modes, then from that you can construct a matrix B with same number of zero modes. But if you consider the element wise transformation, which is separable, then your zero modes, they will be localized. So using that theorem, we can pick out these Qij's in this way. This is just one of the example. One can take other functions to localize it. So with this, what we are getting is, we are getting one graph which is producing three zero modes which are localized. Now, unlike clockwork, so clockwork, one chain produces one generation. So to produce three generation masses, you take three different chains and they are independent to each other. You can take whatever different number of nodes or different Q parameter, but we don't have that freedom here. We cannot introduce one more node here, 16th node or something, because this is found by that fractal pattern, fractal transformation. Plus, we have only one parameter f here. We don't have three parameters there. So we cannot localize our zero mode as what we want. So there is these models are very constrained. We cannot just get any numbers out of this that we want. But still, when we look at the zero modes, the localization of the zero modes in these patterns, we see that, for example, we have given this one left and one right zero mode. So there are three of these. Now they will be localized. So because of the factor of Q that we have chosen. Now the other fact is that these zero modes, there are three zero modes, so they are localized at each node by different extent. So one is localized at, let's say, 15th site, one is localized at 14th site, and if you're looking at their contribution on 7th site, so they will have different amount of overlap or the component on that side. So naturally, what you're getting is different extent of localization of zero mode just by one structure. So you don't need to consider different independent structures and then consider one structure to explain one mass in their mixing. You can just take one structure, it will say you have three modes which are localized, and then you can produce three different mass scales naturally. The below 3D diagram, it shows the localization of zero mode. So in the context of, if you consider that Sierpinski triangle, so that's how they're localized. And as you can see on somewhere the 8th node, they have some component, some overlap is there. Now, once you have these properties of these zero modes and they're produced and they're localized, then what you can do is you can again couple your Higgs on some of these sites. Now we have chosen these sites, and it turns out that when we choose these sites, these three zero modes which are produced, they have different extent of localizations. So they are producing three different mass scales naturally. So to come to the numerics, the results that we got. Now, in principle, this fractal can produce three different mass scales. It can also account for three intergenerational mixing, because at each node their zero modes have some components, so zero modes can mix among themselves too. So in principle, this can also account for intergenerational mixing and their different mass scales, and also why there are three flavors. So if you look at the numerics, so this is done, the order calculation is done. So we were trying to see if for the lepton sector, charge lepton order mass ordering can be produced. So we were able to produce the GeV, 0.5 GeV and 1 MeV mass scale, which is of the order of lepton, muon, and tau. And we know that they don't have any mixing, so we can find the parameters where there was no mixing, but these mass scales are also produced. And this plot that we have shown here, this is a plot which shows that how these three different mass modes or zero modes that are produced, their scale varies how with the parameter y, z, and f. So what we think is that if we increase the value of f, our localization of the zero mode will increase. So if there is more localization, we can think that the mass scale is going down. And that is what we expect, and that is what we get. As we move from left to the right, we're saying those mass scales, this is log of mass scale on the y-axis, so it goes down. Now, if it is written 20,000, it's not the value of f. The value of f there is 2,000. You have to divide it by this, or sorry, 2. You have to divide it by a factor of 10,000. And if you look at 40,000, the value of f is 4. So you see, by the value of f equal to 9 or 10, you are getting a mass which is 10 to the minus 12 order suppressed from the fundamental scale mass. So with the natural orderings and natural parameters at the fundamental scale, you can account for the hierarchy masses too. Now, the problem is that if you localize your zero modes too much, so since they are localized too much, they don't have very much mixing among them, then their mixing will go down. But to produce neutrino masses, we know that they have to be very much suppressed, because if you start from TeV or even Higgs wave scale, you need 10 to the 12 order or something like that, GeV order compression. So that requires a big localization, but that requires a large mixing from experimental side. So this can be done. We can not go as far as 10. We can restrict ourselves to around 4 or 3. There the mixing is large. We can get the PMNS mixing, and at the same time, to lower the scale, we can use those Y couplings. Now we have tried to account for these quark sectors too. So in the quark sectors too, we were able to find the parameters F and Y's, which were able to produce the quark masses and their mixings, the CKM mixings, except for the top mass. So to give the summary, standard model has these 3 generations of particles. So particles, they come in 3 copies, and they have different mass scales, and they have intergenerational mixings. Now people suspect there might be some more fundamental physics which is going on in there. So they come up with some other mechanisms. So we tried to use fractals for this fact, because fractals have connectivity. And so we were capable to produce these intergenerational mixings and these mass with the help of just 1 graph. We didn't need 3 generations. So as an example case, we took Sierpinski fractal, and it was able to produce the leptons and quark masses and mixings. So with that, I've left. Thank you for attention.
Thank you for the nice presentation. So quick questions. Yeah.
Yes, it's come out of calculation. Yes.
Okay.
Where does it come?
Okay, so the origin is that we have these 3 Y parameters and that F parameter. So F parameter is the localization one. So if the localization is strong enough, we know that our 0 modes will not take. So
Question from.
yeah, here we haven't considered CPU as special case.
Okay.
Not.
So analytical expression. So okay. Yeah, so okay. I mean, it's a 15 by 15 matrix, so we were not able to exactly compute the analytical expression, but we did it up to some approximation. So some perturbative approximation, we have that formula in. I don't think I have it in the slides. Yeah, you can derive it. Yes. Yes.
Okay, so let's start. Any question, comments from audience who are not here? Okay, so let's move on to the next talk. Okay, let's thank the speaker again and move on to the next. Since we are running late, let's be very quick. Where is the other speaker? Thank you. I would speak on the role of Large Hadron Collider detectors in distinguishing astrophysical neutrinos from antineutrinos and its implications.
It is not full screen. Control L, I think. Will do. Yeah, thanks. Okay, so let me first thank the organizers for the invitation to attend this conference. And I'm especially glad to give a talk in which, in a conference in which you are also remembering Professor Rajashekaran. So he was my teacher. I was an undergraduate student at CMI, and he taught us along with Professor H.S. Mani. He was, and many other faculty members at IMSC at that time. They were leading the physics program at that time, and he taught us 2 courses. I remember one on quantum mechanics, and then one in the final year on special and general relativity. And not only the courses, he encouraged us in many different ways and helped us in many ways. And I especially remember, so Professor Murthy's talk title, it had this inward bound, and he insisted that we should read the book Inward Bound by Abraham Pace to learn about the history of quantum field theory and particle physics. So I'm very glad. And although I'm not an expert in neutrino physics, in fact, this is when this paper comes out, this will be my first paper on neutrino physics. But I decided to talk about this because, as Professor Murthy mentioned, towards the later half of his career, Professor Rajashekaran was very much involved in this INO project, which was a magnetized iron calorimeter experiment. And the large collider detectors that I am going to talk about are also of the same type, but of course much smaller in size. And today I will not talk about astrophysical neutrinos as such, as the title said, but only about atmospheric neutrinos. So this talk is based on this paper, which is probably going to come out this week. And I must mention that most of the hard work has been put on by Deep Ghosh, who just finished his PhD last year with me at ISCS and now is a postdoc at ISAR Kolkata. So since the audience is broad, let me first review a little bit about atmospheric neutrinos. So atmospheric neutrinos are produced in the interaction of primary cosmic rays, which are mostly protons and a little bit of other heavier nuclei with the air molecules in the atmosphere, which is mostly nitrogen and oxygen. And depending on the energy of the primary proton, the different mesons can be produced in these interactions, like pi mesons, k mesons, and so on, which subsequently then decay to generate a flux of atmospheric muons and neutrinos of different flavors. Now, at low energies, the most copiously produced mesons are charged and neutral pions, where the charged pions and neutral also, they decay before reaching the sea level. So if you consider a 10 GeV pion, it travels only about half a kilometer before decaying. And a positively charged pion will decay to give a muon and a muon neutrino, while a negatively charged pion will give a muon antineutrino. Now, muons also decay, but with a much longer lifetime. If their energy is less than around 2.5 GeV, they will decay before reaching the sea level. So the atmosphere is around 15 kilometers high. And for muons with energy larger than this value, they don't decay before reaching the sea level, and therefore their decays do not contribute to the neutrino flux for those energies. Now, if you put these things together, then you see that at lower energies, when the muons decay before reaching the sea level, for both the positively charged pion and the negatively charged pion decay chain, you produce a muon neutrino and a muon antineutrino in equal amounts. So the ratio of muon neutrino to muon antineutrino is order 1 up to a GeV or so. If you go to higher energies, as we just discussed, the muons do not decay before reaching the sea level, and therefore this ratio starts to increase because positively charged pions are produced more often than negatively charged pions. And this has to do with the valence versus sea quark PDFs. At even higher neutrino energies, the K mesons start to become important, and they are produced in large numbers and with more K plus than K minus. And if you look at these decay branching ratios of K meson, you see that most of the time you will produce a muon neutrino. Therefore, putting all these facts together, this ratio of muon neutrinos to muon antineutrinos, if you average overall zenith angles, will be around 1.2 at 10 GeV of neutrino energy, and it will grow slowly with energy. So it will be around 1.4 at an energy of 100 GeV or so when kaons become important, and even higher at higher energies. These numbers are obtained by using certain flux models, the famous Honda flux model. And I will discuss how different flux models differ later on. Well, in this slide itself. So these are the different fluxes and flux ratios. So if you look at this first figure on the top left. It shows the muon neutrino and muon antineutrino fluxes averaged over all directions. And with energy, you can see that the difference between them is increasing, which is further shown in this ratio plot down here. And the important thing to note here is that if you compare the muon neutrino to muon antineutrino flux ratio predicted by different models, then they differ quite a lot at higher energies. So at energies about 100 GeV or so, they differ quite a lot. At lower energies, the differences are smaller. These, of course, come from lack of knowledge about fragmentation functions and so on that are involved in these models. So given these significant uncertainties in the muon neutrino flux ratios, it will be interesting and probably important if we can measure this in experiments. So that is the goal of this talk. Now, a brief remark about atmospheric neutrino detection. So although neutrinos are the most abundant cosmic rays at the sea level, detecting them is very difficult because of the small neutrino nucleon cross section. So if you average over neutrinos and antineutrinos, the charge current cross section is around 10 to minus 38 centimeter square times the energy of the neutrinos in a broad energy range. And the flux of neutrinos around the GeV, if you sum over all directions, is around 1 per centimeter square per second. Okay. So if you put these two things together, then the interaction rate for a 1 GeV neutrino, which is the important quantity for the detectors. So this is the flux, 1 neutrino per centimeter square per second. And this is the interaction cross section per nucleon. So given this small value of the interaction cross section, you need a large number of nucleons to have some events. And if you put together a kiloton of material, that's around 10 to the 32, 6 times 10 to the 32 nucleons. But that is also not sufficient. You need to wait for a long time. If you wait for a year, you expect around 100 neutrino interactions per kiloton year for a 1 GeV neutrino. Of course, the flux of the atmospheric neutrinos fall very fast with energy. So at higher energies, you have much smaller numbers. So the takeaway from this classic estimate is that to study these charge current interactions of neutrinos that we are proposing to study, we need a detector at least a few kilotons in fiducial mass, and it should run for at least a few hundred life days. And in addition, to distinguish neutrinos from antineutrinos, which we wish to do using these charge current processes, we need a detector that can distinguish between charged leptons and charged antileptons, and then possibly with a magnetic field. Now, both these conditions are met by a detector that operated earlier, which is the MINOS experiment. Although MINOS was operated primarily using a neutrino beam, it carried out a study of atmospheric neutrinos as well when the beam was off. It had two detectors, a near one, smaller one, and a far detector, which is much larger. The far detector had a weight of around 5.4 kilotons, but around only 4 kilotons fiducial mass was available for atmospheric neutrino studies. It had a magnetic field of around 1.3 Tesla in the far detector, so they could distinguish between neutrinos and antineutrinos. And they made measurements of the atmospheric neutrinos for about 2,553 live days and had a significant statistics around 2,000 candidate events of different types, which I'll discuss later. And based on these events, whether the events were of content vertex type or whether they were induced by the rock below the detector, they obtained this ratio of muon neutrino to antineutrino, or rather charge muon to minus charge muon to plus charge muon to about 2.2 or 1.6 with different statistical errors. However, the energy dependence of the ratio that I emphasized earlier was not reported by the MINOS collaboration. Now, what we are proposing to do is to use the ATLAS detector at the LHC for the same purpose. So ATLAS is the largest collider detector that has been ever built. It has a length of around 44 meters and a width of around 25 meters and weighs 7,000 tons. There are two magnet systems, 2 Tesla magnet for the inner detector and 0.5 Tesla in the barrel region, and in the end caps around 1 Tesla for the muon system and calorimetry. And the important thing to note, given this estimate that we had of the mass required to detect atmospheric neutrinos, is the fact that the Atlas hadron calorimeter, which is mostly iron, has a weight of 4,000 tons, 4 kilotons. This is a cross-sectional view of the Atlas detector. The central line is where the beam comes from, and it collides at the middle point. And on both sides, there are tracker elements of a meter, a little more than a meter in height, followed by electromagnetic calorimeter of a similar size, and then a hadron calorimeter of height around 2 meters, followed by a muon chamber, which is around 7 meters on both sides. So the muon chamber defines the shape or the span of the detector, and they are rather large. So, so the first requirement is met by Atlas. It has a large fiducial mass. How about the second requirement of the time required? Now, the LHC beams are not in circulation during the winter months, while the detector and the magnetic fields are on during most of this period. They are on for different reasons, for example, for cosmic ray studies and for detector alignment and other checks. So if around 100 days per year are available with the detector and B fields on, but the LHC beams off, then in 10 years, you can have 1,000 live days for doing such neutrino physics. If instead only 60 days per year are available, you will need a longer period, around 15 years, to have the same statistics. Now, given the very long timeline of the LHC and the HL-LHC, these 10 years and 15 years periods are certainly feasible. So what kind of events do we expect to see at Atlas induced by atmospheric neutrinos? There are, for content vertex type events, there are two distinct possibilities. One is that, so let's consider downward going neutrinos. So these downward going neutrino might interact either in the upper part of the hadron calorimeter or in the lower part of the hadron calorimeter. If it interacts in the upper part of the hadron calorimeter, then it will pass through the tracker, the produced muons in DIS will pass through the tracker elements and then go to the muon chamber. If on the other hand, this neutrino interacts with the HCal material on the lower half, then it will not have any tracker elements and it will directly go to the muon chamber. Same thing for neutrinos going upward, so passing through the act. And there are two types of events, one for which both the tracker and the muon chamber information are available, and the second category for which only muon chamber information is available. So for low energy muons, we definitely need the tracker information because they don't go much far in the muon chamber to learn about their momenta and the charge by bending in the magnetic field. So for low energy muons, we can only use events where both the tracker and muon chamber information is available, whereas for high energy muons, only the muon chamber information is sufficient. Right? The length of the muon chamber is sufficiently large so that from the bending in the magnetic field, we can know both the momenta and the charge of the produced muons. Now, how about backgrounds? So the Atlas detector is not sitting at a very large depth. It's around 100 meters only from the ground. So cosmic ray muons are a large background. However, the distinct event topology helps in reducing the background. Consider, for example, a cosmic muon entering from the, so muons, cosmic muons always enter from the top and go down. Okay, so they're always downgoing. So this is how a cosmic muon trajectory will look like. However, for the signal, the neutrino travels a long distance, 7 meters, into the detector and then converts into a muon in the HCal. Therefore, these downgoing cosmic ray muons cannot mimic downgoing content vortex atmospheric neutrino signals. Right. So these cosmic muons will necessarily hit the muon chamber first and then go down. But these muons will not hit this upper part of the muon chamber. It will only hit the tracker elements and the muon chamber downstairs. What can be problematic is the second type of events where these neutrinos come, travel to the upper part of the hadron calorimeter and then become a muon. That might be mimicked by a cosmic muon which doesn't have a large energy and which stops at the hadron calorimeter, right? In that case, these tracks look similar. However, the LHC has very good timing ability. In particular, the muon chamber has these RPC plates which have a timing resolution of 1.5 nanoseconds. And to travel this 7-meter distance in the one part of the muon chamber, a muon takes about 23 nanoseconds. So we can decipher whether the muons are hitting the upper muon chamber plates first or the lower muon chamber plates first. And by using this timing information, we can also veto this kind of cosmic ray muon events. So all in all, the conclusion is by either using the special topology of the neutrino events or by using the timing information, excellent timing information that is available with these detectors, we can eliminate cosmic ray muons even though the detector is not sitting at a very large depth. So now what about the event rates? So to know the event rates, let me briefly recall the neutrino-nucleon cross sections. And here the main point to note is that neutrinos have larger cross sections than antineutrinos with nucleons, right? So there are different types of processes possible: quasi-elastic, resonant inelastic, and finally deep inelastic. It is deep inelastic which dominates from a few GeV or so for neutrinos and from around 10 GeV or so for antineutrinos. But in all cases, the neutrino cross sections are larger than the antineutrino cross sections. So it is a deep inelastic that we shall focus because we will be dealing with mostly higher energy neutrinos. And so this is a approximate expression for the neutrino-nucleon deep inelastic scattering producing a mu minus and anti-neutrino-nucleon deep inelastic scattering producing a mu plus. And the quark contribution for the neutrino scattering is not helicity suppressed. So this is the quark contribution, whereas the anti-quark contribution is helicity suppressed, and conversely for the anti-neutrino case. And that leads to this difference in the cross sections that I mentioned. Now, when the muon energy becomes close to the neutrino energy, then this helicity suppression is lifted and the cross sections become of the same order. But as the energies are different from the neutrino energies, so this y goes towards 1, the cross sections differ widely. So these two facts together will decide these muon numbers that we observe in the detector. So there is a twofold enhancement of the muon to anti-muon number, right? First, the flux of muon neutrino to anti-muon neutrino, and then this cross section factor which is larger for muon neutrinos compared to anti-muon neutrinos. So putting them together, these are these content vortex events that Atlas may be able to observe if you have this 1000 live days exposure that I mentioned, which is 11 kiloton year exposure. And this is the distribution of the events for these kind of events as a function of energy. For energies larger than 3 GeV, so we start at 3 GeV because we cannot do muon physics at LHC below 3 GeV. A muon with energy less than 3 GeV doesn't reach the muon chamber and so cannot be identified as a muon. So we start from 3 GeV onwards, and these are the muon numbers and anti-muon numbers expected for all the events higher than 3 GeV. So these statistics is not so bad. And if you take the statistics, the ratio that we discussed in the beginning comes out to be around 1.9 or so. However, these events are without this selection criteria that I mentioned. We must impose the selection criteria that the muons should go through the tracker elements and the muon chamber if they are of lower energy, and if they have higher energy, then both kinds of events can be accepted. So, and of course, they have to be in the rapidity range of 2.5 or so. So if you impose those selection criteria, then between 3 to 10 GeV, you have around 31 mu minus and 17 mu plus. So the statistics comes down and we will be dominated by statistical errors. The ratio comes up to be around 1.8. As you go to higher energies, the ratio increases, as we discussed, it should. However, the statistics become poorer and poorer for these content vertex type events. So to improve the statistics, we have to take help from these external upward going events that I mentioned for MINOs. So this is the Atlas detector. Of course, it's not to scale, and this is the Earth. And for the neutrinos going from down, they can interact anywhere in the rock column and produce a muon, which will then travel to the detector. Now, the range of the muon, the distance that the muon travels depends on its energy. So, higher the muon energy, higher distance it travels, and therefore the volume of the rock column is larger and larger. So, taking into account these kinds of events will increase definitely the statistics. However, the events are less striking compared to these content vertex events that I mentioned. Now, if you compare the signal and the background, so the signal here is the neutrino converts to a muon somewhere down here and then the muon travels to the detector, and this is a cosmic muon. So, the only information that you have to distinguish between this signal and the background events is the timing information. So, for cosmic ray muons, they will first hit the upper muon chamber and then the lower muon chamber, whereas for the signal, it will first hit the lower muon chamber and then the upper muon chamber. So, for these events, as I said, the statistics is much larger. These are the distributions as a function of energy for mu minus and mu plus. And as you can see, above a 3 GeV or so, you have around 700 mu minus and 341 mu plus events, which is pretty large, and the ratio is around 2. So, as I mentioned, the higher energy neutrinos contribute to these kind of events. Therefore, the ratio of mu minus to mu plus expected is also larger for the reasons that I explained earlier. The flux also grows as a function of energy. And as you can see, even if we go to higher and higher energies, we still have sufficient statistics with these upward going events, and we can study the energy distribution of this charge ratio using these external upward going events at the Atlas successfully. So, this is just a final summary plot which shows the mu minus to mu plus ratio as a function of energy, which, as I said, MINOS didn't report, but Atlas has the capability to measure. And this is for the content vertex muons. We can only go up to energy of 20 GeV or so because the event rates fall so fast and it grows with energy in the way expected. Whereas for these external events, we can go easily up to 100 GeV or so, after which the statistics is not good enough to get the ratios correctly. So, that is the summary of the study. So, to summarize the whole thing, the ratio of atmospheric muon neutrinos and antineutrinos, as I tried to emphasize, is an important quantity. And there is still a large uncertainty in its prediction in the flux models, especially at higher energies. And therefore, it is important to be able to measure this ratio directly in experiments, in neutrino physics experiments, as a function of the neutrino energy. However, most neutrino detectors do not distinguish between muon neutrinos and antineutrinos, simply because they do not have a magnetic field, which magnetized detectors can do in an event by event basis. So, detectors like Super Kamiokande with gadolinium and so on put in can statistically figure out antineutrinos up to energies of 10 or 20 GeVs, but not in an event by event basis. So, magnetized detectors can of course do that, and MINOS has done that up to a good level. So, the point of this talk was that we already have large collider detectors like the Atlas the CERN LHC, which have the fiducial mass required. So, around 4 kilotons for the Atlas Hadron Calorimeter, and they are extremely finely instrumented. Because they are small and collider detectors, they are much more finely instrumented than large neutrino detectors. And because of this fine instrumentation, even if they are not at a very great depth, they can reject cosmic muon backgrounds. So we have a finely instrumented large enough detector to do some neutrino physics. So we should do it. And in more detail, what I showed is while content vertex events are very striking, they do not have enough statistics at high energies, but these upward going events, which are produced in the rock column below, have a much larger statistics and can determine the energy distribution. So I end here and thank you.
So thanks, Sathya. There are too many questions. Okay, maybe we can start from first row. So let's have a brief question so that.
Okay, so yeah, that's a nice work. But how do you determine the charges of the muons?
There's
so
a field. So from the bending. So
from the muon chamber bending or from the tracker?
both. I mean, depends on what it passes.
But yeah, if it is from the tracker, then probably we will not be able to do it because the tracker volume is smaller.
Yeah,
Right?
I showed that. So it has to reach the muon chamber to be called a muon, and then you have a large arm length.
Mhm.
And then from the bending, like measuring the sagitta of that, you can know the charge. So it's a standard muon charge determination. So it has to reach the muons.
Sure.
Nice talk, Shruto. If you go back to the previous slide, yeah. So I'm curious. So there are two sources of this ratio not being one. The first is, as you said, that there are, there's an overabundance of, let's say, muons over antimuons or whatever, and the other is the cross section is different. Now there are errors that will come from statistics. There are uncertainties that will come from the statistics, and uncertainties that will come from the lack of knowledge of the cross sections themselves. So yeah, the systematics. So once you fold that in, at what, let's say, statistical accuracy can you establish that you've discovered the original asymmetry between muons and antimuons?
Right. So the dominant uncertainty is actually in the flux, not in the cross sections. So the cross section uncertainty is of the order of 5% or so at higher energies. And whereas the flux uncertainty can go from 15 to 20%. So which is what we are trying to pin down by doing this.
You can
So
put it the other way around, no? I
Yeah.
mean, you put in the model, right, which has a flux ratio of something,
Right.
and you're getting out a flux ratio of something. So how different are the two? That's really, I think, his question. Also my question. I mean.
Well, I mean, I thought he's asking how much the cross-section uncertainties also matter. And
That's
so,
what
the,
you're
yeah.
thinking of this up, right?
Right. So of course you can compute using different flux models and then make an estimate of the uncertainty in the prediction from the flux models.
In this model, you have put in 2 and you're getting out 2, is it? You put in some flux.
No. So the flux model goes only, the model that we have put in only gives you around 1.5 in the flux ratio and higher energies.
Whatever you put in, you should get out, right?
No.
That's what is.
But then there's a cross section also on top of
You should
that.
be able to extract it.
Yeah. So the question is, can you deconvolve that part?
So you see what I'm plotting here is R mu minus by mu plus only, right? I have not gone back and plotted R nu mu by nu mu bar. Further, I have to do the unfolding. So that unfolding has not been done. So given a flux model, given a cross section, this is the prediction. You change the flux model, you take into account the uncertainty in the cross sections, there will be a band, right? So what that band is, I do not know, but as I said, the cross sections have an uncertainty of around 5% or so at higher energies, and the flux models have an uncertainty of 20% or so, right? And so the question is whether the measurement can reduce the flux model uncertainties by being a new input, right? So for example, the muon charge muon to minus charge muon to plus charge muon ratio, right, at sea level, that's an input to these flux models. What we are trying to propose is this can be an additional input to the flux models. Yeah. Rock events have a larger statistics, of course. Okay.
Yeah, I have a different question. So this is an interesting idea. But have you talked to people on Atlas at all about the triggering of these events? Because I think the contained vertex would be a new trigger.
Right.
And the external upward going events should already be there in their existing cosmic data, I think.
Right. So that's a very interesting point. I did talk to several experimentalists, all of them in CMS, because in India we mostly have CMS people. In particular, I talked to Professor Sunanda Banerjee, who is one of the leading experimentalists in CMS. He said the triggering is certainly possible. So it will be done with a single muon trigger. And as you said, data already exists with single muon trigger. But somebody has to go and look into that data and see whether you have such events. And he also told me that doing the analysis with beam off, but the detectors on and the magnetic fields on for around 2-3 months a year should also be possible.
Hi, thanks for the nice talk. I have a sort of a nice question. So one problem, one input that you need to calculate is the atmospheric neutron flux at these latitudes and at these geomagnetic levels. And that varies. It also has a function of the zenith angle. And I think that is not there for the CERN site.
Correct.
So that will bring an additional uncertainty that has never been done at the CERN site. So that has to be redone if you want to do this thing.
I agree. So, I mean, I just use the standard ones, and the fluxes that I used are for the Kamiokande site.
Yeah, but
no,
it can change.
So it's 100 meters, and and the zenith angle dependence also was not studied here so far.
Yeah.
So I used an average flux over all zenith angles. But yeah, the site may matter, and we don't have a flux per CERN site. So
Okay, thanks.
Yeah, so then Kamioka should be good. I mean, I randomly picked up Kamioka, but yeah, thank you. Yeah.
Okay, yeah. Is there any question from
Who are not in here? Okay. Thank you. So let's break now for coffee, and let's come back at
So, but I don't think I need this. No, for the online people, you need it. Yeah. 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 Online. Yeah.
It's a great pleasure to have our good friend V. Anandarayan here. He'll be talking on Feynman integrals and hypergeometric functions, recent results and mathematical implementations. So welcome, Anand.
Yeah. Thank you very much. It's a great pleasure to be here to be talking at this workshop, which is also in the memory of Professor Rajashekharan. I'm going to be talking about some research that we have carried out and also present the results. And in the spirit of today's era of management, we actually have deliverables in the form of several codes which are now published and available for the public. One of the people who has been instrumental in the development of this work, my former student Ratan Sarkar, who's a postdoc here. Also, many of my earlier students have also been in IMSC, Gauhar Abbas and late Im Song. So I'm very grateful to IMSC. Very pleased to be here with all this great facilities, also the refurbished guest house. Pleasure to be back. Okay, so let me now talk about a couple of different things. Most of the considerations here are elementary in the sense that these are things that one can explain to anybody who's had an education up to final year BSc or even first year MSc. But we have to put all these things together in order to get a hang of what is going on with Feynman integral evaluations and also hypergeometric function theory, which is often taught first year MSc or a little later. But the interaction is quite complicated. And as we started our researches, we discovered that many of the implementations in Mathematica or any other kind of package is highly inadequate. So that's the reason why we had to actually generate many of these packages, which are now published. As a representative of some of the packages that we have written, I'll be talking about three recent ones. One of them is called Fein GKZ. This is, of course, involves Feynman integrals. And GKZ are three mathematicians, Gelfand, Karpanov, and Zelewinski, and they had analyzed hypergeometric functions. And recently, a couple of papers talked about how Feynman integrals can be viewed as GKZ systems. But there was no computer algorithm implementation, so that was done. And another package that we wrote is named after an author who first wrote a paper in 1964 or 66 on how to get various analytic continuations of hypergeometric series. As we all know from our MSc education, it's not enough just to say something is a series, but you also need to know the regions of convergence of such series and to be able to get suitable analytic continuations. Simplest example is 1 plus x squared, etc., which sums to 1 by 1 minus x if mod x is less than 1. But supposing you want to know the series also for x greater than 1, then you can write it as 1 plus 1 by x plus 1 by x squared. That's an elementary example of an analytic continuation, which you know how to do. So those are the important issues in hypergeometric theory. And this is of importance also to Feynman integrals, because in Feynman integrals, the variables are various ratios of masses or ratios of squares of momenta and masses. And you don't know for your physical problem what will be these values of these variables, whether they lie in the region of convergence of the original series or not. So you may need analytic continuations for the particular problem that you have in mind. So this also allows you to do this for hypergeometric functions with more than one variable. And one important example is known as the Appel function, which is a generalization of the Gauss 2f1. Okay, so let me start with a few examples and a few definitions, very simple. So these are all present in textbooks. One of them is a Pochhammer symbol, which is given by x. Pochhammer symbol of x with this index n is nothing but the ratio of gamma of x plus n by gamma of x, which for values of x which are integral actually terminates after a while. It's a kind of an incomplete gamma function of this. I shouldn't say incomplete, it's called a rising or a falling factorial. We also need a definition of the Pochhammer symbol of 1 with n, which is factorial n. So the Gauss 2f1, the basic function that he studied, which is a generalization of the series 1 plus x squared, etc., is something that looks like this. It is denoted by 2f1. Why 2f1? Because the 2a and b stands for the two Pochhammers that appear in the numerator over here. And the 1 because there's only one c which appears in the denominator over here. And if you just write out the series, you can see that it's an elementary extension of the geometric series that we all do in high school. So this is 1 plus a times b divided by c times x plus a times a plus 1, c times c plus 1, b times b plus 1. You see, you can see the Pochhammer structure arising over here, and then various other factorials over here, like so. So this goes on. And Gauss also, he was particularly interested in this function because he was interested in studying the differential equations satisfied by this. And this satisfies the following differential equation. You can immediately see that it has 3 singular points at 0, 1, and infinity. So in our work, we will have to extend the Gauss to F1 to hypergeometric functions in more than one variable, which means that such a hypergeometric function, if it exists, will satisfy partial differential equations in each of those variables. Okay. So, and if you have 3 singular points in this case, if you went to 2 variables, you would have singular curves. If you went to, say, a hypergeometric function in 3 variables, then you'll have singular surfaces, etc. So that is the theory of hypergeometric functions. The other very nice thing is that this also satisfies an integral representation, and I want to draw your attention to the structure of this. So once again, let's keep in mind that there are 3 variables, that there are 3 parameters a, b, and c, and 1 variable x over here. Now, Feynman integrals will often look like hypergeometric functions of this kind, where the x will be ratios of masses and momenta, and a, b, and c will contain the dimensional regularization parameter epsilon. Okay, so there's also a nice separation of the features of dimensional regularization and the physical kinematic invariance like this. Why is that? There's no real obvious reason. Murthy today mentioned Regé dynamics. Actually, Regé wrote a paper in the 50s, which is the fundamental paper, which shows the relationship between hypergeometric functions and Feynman integrals. As usual, very far-sighted paper by Regé. And a lot of the developments later also came from that, including the GKZ developments and so on. Okay, so here let me again introduce some more definitions which are not very important, but this integral representation is very important for us. I would like you to observe that this a, b, and c, the parameters appear as exponents over here, and then there is a dummy variable of integration t. The variable x is sitting along with this, whereas the a, b, and c sit as powers over here. Now, in order to actually extend this to hypergeometric functions of more than one variable, we will require this kind of integral representations where these variables t actually will become things like the Feynman parameters of Feynman integration. So that is a connection between GKZ systems, the integral representations, and Feynman parameters. Okay, so these are the basic properties of these things. So, let me go on here and find a more interesting analytic continuation of 2f1 about 1 by x, which is the analog of what I had mentioned earlier about getting analytic continuation of 1 by 1 minus x. So the thing is that on the right-hand side in this non-trivial example, you end up with more than one hypergeometric function, 2f1. But in the case of Gauss, this actually closes in 2f1. You don't need anything else. Let's also keep in mind that this could have been readily generalized to pfq, that you may have had p such parameters in the numerator and q such parameters in the denominator, and that is called pfq, which was also studied in the 19th century. And then there are analogs of this for hypergeometric functions of 2 variables. Also, very important property is satisfied by these hypergeometric functions known as the Pfaff-Euler transformations, which look like this. Now, all these are things that we are going to be using when we write our Mathematica code. So the next step is to actually get generalizations of Gauss to more than one variable. Let's call them x and y. Okay. So Appel in the late 19th century studied 4 of them. He was able to find only 4, which are actually truly hypergeometric. There's also another family of functions known as the Horn functions, which was developed by Horn. So here goes. So now instead of having one index of summation, you'll have more than one index of summation, call them m and n, like so. And then you have the 2 variables x to the m, y to the n. And just like in the 2f1 case, you're going to have Pochhammer symbols like this with a, b, and with, let's say, this a, b1, b2 showing up in the numerator, c1, c2 showing up in the denominator. The other important thing to see is that there's a non-trivial interlacing of these indices over here. It's not just like it's multiplying 2f1s and having indices which don't talk to each other. That would be a trivial kind of generalization of a hypergeometric function of one variable to two variables. This is a non-trivial generalization, and this therefore is seen in the fact that these indices of summation get interlaced, and this is the definition you can see in m+1. This F4 is the most complicated in this family, and it looks like this with an m+1, m+n showing up here, m+n showing up over here. Now, all of us know from high school algebra that if you have a series and you want to test the region of convergence, you can use a ratio test, or you can use the Cauchy test, or Gauss test. Now, there are analogs of that for variables in more than one variable, and this is called the Horn's test, named after Jacob Horn, who actually worked out the theory for regions of convergence of series of two variables and more. Then there are generalizations to n variables. Here I've given the example with 3 variables, Z1, Z2, Z3, with various interlacing of these indices, and these are called the Lauricella functions, like so. This is the most general object. You can keep defining this for more and more, but of course, rapidly becomes far more complicated. Key thing is that there's also a region of convergence over here for this defining series, which is that square root of mod x plus square root of mod y is less than 1. So this is not sufficient for many purposes of physics, and what you need are analytic continuations of this. Now let's just change tracks. Yeah. Yes. They all satisfy various partial differential equations. The key thing is that they are partial differential equations, and therefore far more complicated than just the ODE satisfied by Gauss. The GKZ people are the ones who studied the partial differential equations associated with this, but in analogy to the ordinary differential equations satisfied by Gauss. And that's the system that they have, which is called the GKZ system. And there's a whole mathematical theory which shows up also, Calabi-Yau, and string theory and so on. There are various aspects of GKZ theory that shows up in many different branches of mathematical physics. So here is a basic definition of Feynman integrals, which are, so here is an L loop integral like this, which has L factors of this momentum. And then there's also several propagators. So the key thing is these propagators appearing in denominators raised to various powers. So this is a Feynman integral, period. Okay. So these are the objects of interest to us, depending on different masses, different external momenta, and different powers raised over here. So these are a family of Feynman integrals that are called scalar Feynman integrals. In principle, these could also be multiplied by various factors of momenta, external momenta, internal momenta, etc., etc. But it suffices to study only scalar integrals, because all the rest can be re-expressed in terms of scalar integrals. And those which you actually need are what are called master integrals. And there are plenty of masters in this audience who know far more about them than I do. Various examples. Here's a tadpole, which is a simple one loop integral like so, no external momentum entering. Here is a bubble, one external momentum entering. You can have two different masses in just an integral over here. Here's a one loop triangle. Again, there's only one independent momentum because of momentum conservation, but you have 3 propagators over here. So here are simple examples, one loop, and by now there are theorems which say that these actually involve at most polylogs. Whereas already the simplest possible two-loop diagram, so-called sunset diagram, which has one external mass, one external momentum and 3 internal masses, already no longer falls under the category of polylogs, but actually generates what are called elliptic polylogisms. So here are examples of Feynman integrals which actually satisfy something called differential equations. There are many experts over here. There's a differential equation satisfied by this bubble. And then here is another bubble and a tadpole. But the key thing that I would like you to observe over here is that the boundary condition over here involves the 2f1. You see, I've been saying so much about hypergeometric functions without even ever giving you an example where on earth these are coming from. Here is an elementary example of what this 2f1 is. Here are more examples. For instance, at one loop, we know that there are objects known as the Passerino-Veltman functions, A, B, C, D, etc., which need to be regularized and evaluated and so on. Here's a simple example where the B0 function, which is just a 2-point function with 2 unequal masses, M1 and M2, actually evaluates to an F4. Now this, in many textbooks, you will find that these are written in terms of logarithms or well-known functions, but actually there's an underlying Appel function F4, which is related to other known mathematical functions for specific values of these parameters. This is an example. Here's another one loop example of 3-point functions, which involves the Appel F2 over here. And for instance, the sunset which I just showed you with unequal masses involves the Lauricella function like so, as it should, because there are three variables over here. I mean, there are three masses and one square of a momentum, and therefore you have three independent ratios, call them Z1, Z2, Z3. But the defining representation is only in the small unit diamond as far as these things are concerned. So, for instance, if your kinematic configuration corresponds to this red spot over here, your defining diamond is only this golden thing object over here, and the series cannot be used to evaluate your object, which is this red point. So, in order to go there, you actually have to have an analytic continuation of the F2 using various techniques, analogous to what I had shown for the 2F1. Of course, it's far more complicated, and so you need algorithms to do that, and that is one of the things that we achieve. So in our work, which is a large amount of work done, first the pioneering work was done by Ratan over here in Aspire, along with Abhishek Pal, who was an undergraduate student, Sunetra Ramanan across at IIT Madras. We had this paper. So this is one of the examples that we did, and we invented an algorithm known as Aspire to actually implement what is known as the method of regions using a Mathematica program. So here's an example of pi k scattering, where there are many, many different kinds of kinematic invariants, unequal masses, etc., etc. And we were able to confirm the results that had already appeared in the literature. So this fine GKZ I'll talk about a little bit more. Here's another package that we wrote along with Sumit Banik and our French collaborateur, Monsieur Samuel Friot, and Cheyenne Ghosh, my former PhD student. So here we studied n-fold Mellin-Barnes, and MB here stands for Mellin-Barnes. And the technique used to compute, and this is the key thing, it's an n-fold, not just two-fold, three-fold, n-fold. In fact, the examples that we had even had 11-fold integrals, and we had to find series representations for this. And these very brilliant bunch of young people, they found an algorithm based on something known as conic hulls, which is known to mathematicians. And this is published in Physical Review Letters, but as usual, very painful, because they asked for impact, innovation, and interest, and we had to have a large number of, spend a lot of bandwidth convincing them that this is impactful, interesting, and it is of interest. But not only that, but the referee actually wanted the code, and then later the referee, and we suspect it was Smirnov, who said that he had actually run many of his examples and was satisfied, therefore allowed it to be published. These are the other packages, FaneGKZ and Olson, published in Computer Physics Communications over here, this and this. And Uphell F4 is also, Uphell F2 is also published in computer physics. So my former students, glad to say former students, all except one, they have recently got this paper accepted, where they study various Lauricella functions. And then recently, Shovik Bera has written a single author code, which is called multi-hype EXP. So this is expansion in the powers of epsilon, the dimensional regularization parameter, which is of fundamental importance. If you go back here, you see these epsilons appearing over here in the parameters, it's not appearing in the variables. Therefore, you need expansion in this epsilon if you want the finite part of the Feynman integral. So this is a very useful extension of other known codes from about 10 or 15 years ago, and very successful. So let me say a little bit about this package GKZ that we have over here. I'm already more than halfway through my time. So, what was found some time ago was that any hypergeometric function can have an integral representation analogous to the Euler formula that I wrote. So these Feynman integrals can also be turned into something that look like that kind of an Euler formula. And this was due to a rather recent representation of Feynman integrals due to Lee and Pomeranski. And once it is written in this form given by Lee and Pomeranski, you can translate it into a GKZ system and then try to solve the solutions of the GKZ system. There are various approaches associated with trying to solve the GKZ system. The original that was given by GKZ themselves, which is based on something called triangulations, and I'll give you an example. And all of us, when we do MSc, either as students or as teachers, we always introduce a method of Frobenius. We say that let there be a series solution, you plug it back into the differential equation. Then you collect various terms associated with a given power of the variable. That gives you a recursion relation for the various expansion coefficients. And if you fix some of the early coefficients, then you can solve the recursion relation completely. That's known as the method of Frobenius. There's an analog of that for PDEs also, which is known as a generalized Frobenius method. And we, in our package, we actually implement both methods of this triangulation as well as this Grosvenor deformation or generalized Frobenius method. Instead of saying all that, let me just use a simple example. As usual, let me take this bubble. And then this thing has what are known as graph polynomials associated with that, Szymanczyk polynomials. And in terms of the Feynman parameters for this particular diagram, there are actually only two Feynman parameters, x1 and x2. And then these are the graph polynomials associated with that, which can again be obtained from very elementary considerations. From that, we invent something known as the A matrix associated with the various powers appearing in the sum f plus g, the so-called Lie-Pomeranski polynomial, which is the sum of f and g. So the various powers associated in the monomial basis of x1 and x2 are all assembled in this matrix known as A. And by studying various properties of this A matrix, we can actually generate the entire Frobenius solution. So here is an example where you take this and you plug it in, and then this generates for you various terms associated with that given by an algorithm. It just comes from the Frobenius method. Okay. So this is a bunch of gamma functions, as you can imagine. Then you take this output and then you feed it into the other package that we have written, which is known as Olsen. And then what that does is it resums this and expresses it in terms of the hypergeometric functions. In this case, they turn out to be some of the Horn functions H3, and one of the G1. This is all very beautiful, how such a thing actually all hangs together, and it's also amenable to treatment on suitable Mathematica packages. So this is what we do. And of course, the more other important thing is we also need to discover the regions of convergence of the various series. So that is what we have done over there. It's a complete package that you can download and use, and it's very user friendly. And I think it can be of great use to, people who use this, not necessarily in Feynman integral methods, any kind of mathematical physicist who's studying these properties. So as I mentioned, whenever you study hypergeometric functions, what is of importance is not just having the series itself, but also you have to be able to know what is the region of convergence. So the Olsen package that we have written also has a subunit that is known as ROC2 for region of convergence in two variables. And actually, the buck more or less stops here because there's no complete theory for more than two variables. The Horns, you can have analogs of Horn in higher dimensions, but they are not complete. Only for certain special cases, Horn in 3 dimensions or 4 dimensions actually works. And some of the examples studied by Shovik and Tanay actually are precisely those cases and not other cases. So this is all of, even though it sounds like it's 20th century or 19th century physics, a lot of these things will keep coming back because they have not been settled. And they will be driven by the needs of the community, as in when you have to do these things, you simply have to do it. That's all. So in this Olsen package, you have the option of taking a particular double series, and then you can sum over one of them, and then you produce a hypergeometric function. Then you insert the analytic continuation of this one-dimensional hypergeometric function. Then you re-express it again as a sum, and then carry out this procedure and re-express the result in terms of known hypergeometric functions. But of course, it may not close. In the case of 2f1, I showed you a left-hand side and a right-hand side. The 2f1 on the left-hand side was a sum of 2f1s on the right-hand side. In the case of Gauss, there's nothing else to do, so it happens. Here, there's a lot of freedom, and you may start out with, let's say, an f2, and on the right-hand side, you may end up with more complicated functions or combinations of other hypergeometric functions, or even 2D analogs of the PFQ. Remember, I had mentioned 2f1, which is Gauss. There are also generalizations of that to PFQ. So in 2 dimensions, the generalizations of PFQ are known as the Campé-de Ferrier functions. Campé-de Ferrier and Appel were friends, actually. They actually wrote even a textbook together. So sometimes you may start out with an Appel function, and you may do all this kind of analytic continuation. And on the right-hand side, you may get Campé-de Ferrier. Now, that is real friendship, if you ask me. I'd like to tell all these young people that they have to work together so that one of you does the left-hand side and your pals do the right-hand side. So here's an example of such a thing where various different analytic continuations can be used, or various Pfaff-Euler transformations can be used in order to get these answers. So these are all the options that the package offers. So here's an example let me start out with an F2 and try to get an analytic continuation of this using here, for instance, the analytic continuation about infinity after summing over one of the indices. And on the right-hand side, you end up getting an answer that looks like a complicated combination of this kind. And this is what the answer looks like. So everything that I showed in the previous slide says that you start out with this diamond and you do an analytic continuation about infinity in one of them, and you end up with an analytic continuation over here in this region of convergence. So you can do this again and again, hoping that you will be able to cover the entire XY plane. And it so happens that for F2, you can actually do it, except on the singular lines, obviously, because singular lines, by definition, are places where you cannot have an analytic continuation. So this is a complete package which has been published in computer physics communications. We are also joined with by Oleg Marichev, who's a very well-known Russian mathematician who's now been working for Mathematica for over 20 years. He also joined us in this. So here's an evaluation of this Appel F2. So this is the paper which was also done with Marichev. So here what we have done now, it's very strange that the Mathematica implementations and Maple implementations of Appel F2 actually don't give the correct answer for many different values of the variables. That's the reason why we had to do this. We knew that it's going to appear in Feynman integral calculus, and then it was simply not possible to use any of the predefined definitions. So we had to do this. We were driven by the need to have a reliable way of evaluating these functions. So in fact, there were many numerical problems associated with the fact that you may have seen in the analytic continuations, you get prefactors which are raised to powers of these parameters. Now, if you have something like 1 minus x raised to the power a, and 1 minus x turns negative, then this means that the square root or the fractional power will turn it into a multiply valued function. So you have to define this function in a unique way. And in order to do that, you have to take a lot of care. And that is exactly what we did. And so this Appel F2 function is now a complete package to evaluate this for all real values of x and y. And this is the kind of problems that we have, for instance, to get the unique, correct numerical evaluation using any one of the different analytic continuations. So this Appel F2, it's all described in great detail in our paper, how to get these things whenever you're using different analytic continuations, where there's a danger of the function becoming multiply valued. So this is what I wanted to tell you about. This is sort of like a commercial for the work that we have done in our group, and we would be very happy if this was, used by members of the community. And if you have any questions, of course, we would be happy to answer them. Recently, there's a 900-page book by Stefan Weinzierl. It's called Feynman Integrals. That's the name of the book. It's a must for anybody who is a student of the subject, and definitely a valuable addition to any library. So many of the ideas that I have just mentioned and talked about are actually reviewed in a very magisterial manner by Weinzierl. And there are many other small topics in which he and co-workers have started, but they have not taken it further. So if you're really looking for a gold mine for research problems, I would advise you to invest in this book and probably sell it on the stock market after a couple of years. So many of the things, in my opinion, which are not fully explored are the relationship between dispersion relations and Feynman integrals. There's a paper written by Ettore Remedi. He first wrote his early papers in 1960s, just about 60 years ago, and he continues to write. He has a good paper on dispersion relations and Feynman integrals, but these have not been explored thoroughly. One has to find out ways in which these things can be, enriched so that Feynman integral computations analytically become more tractable. Then there are other ideas associated with Feynman integrals, such as a Hodge structure. This again has to do with the integral representation. This integral representation, if you want to really view it as homological cycles or this or that, which people have done in the 60s, but never took it forward after that, probably it was more complicated. You can look at this. There's a lot of relationship between algebraic geometry, number theory, combinatorics, all these fields, which are all topics of research. So this is because there are a lot of young people in this audience. I just thought that I would mention. Recently, Weinzierl and company have been using something known as iterated Chen integrals, something called iterated Eisenstein integrals also, which are being used by members of the community. And then there's also the theory of differential equations for Feynman integrals. These have all been studied, but whether or not they have been thoroughly studied or not is a question that will take some more time to be settled. And there's something called theory of chords. There are so many things, so many exciting things that one could do. So with these words, I'll stop here and see if there are any questions.
Any questions? Yes, TRG.
See, my stop clock says 30.
I have a couple of questions. One is this famous string theory thing, sigma m is -1 by 12.
Yeah.
Can it be understood in this language? Because that's also analytic continuation.
I don't know. We need to talk about this a bit more. Maybe you can educate me a little bit and then let's.
Okay. There's one more thing is there was some work maybe about a decade back on even in renormalization program on the Forest formula and other things.
Yeah.
That they try to understand by changes in the analytic continuation from one loop to higher loops, etc.
Yeah.
Is it possible to understand it straight from hypergeometric function or many of these things?
It's an extremely interesting question. In our group, even when Ratan was with us, we had tried to look at some of these things, but rapidly became very complicated, and we stopped to see the forest for the trees in that particular sector. So we have not done it. One of our former undergrads, he has now gone off to Hamburg, but he has just put a paper on the archive a few weeks ago with Franz Herzog and this guy, Mriganka Mauli Chandra, whatever, Mriganka Mauli Chakravarti, that's his name, MMC for short. And Herzog, they have a paper where they're looking at these things, and there are all kinds of properties associated with these Feynman integrals. There are Hopf algebra methods, which allow you to do some of these things. In my opinion, none of them has really allowed us to simplify anything. Probably it's a different way of doing the same thing or moving the complexity from one bin into another bin. So I think it will take some years before all these things settle down. A lot of very interesting developments.
There's also the divergence which will come from some of the m mass parameter going to 0.
Yeah.
Like infrared divergence.
Yes.
Is it seen in these things?
It can be seen. All these things, various limits exist and so on. Yeah. And also many of the results that I give are for these parameters when they are non-integral. So the issue of, of their, what happens to them for integral cases is actually a problem. I gave this talk. I become a one-man traveling circus. I gave this talk in Bonn, and there was this person, Albrecht Klemm, who's a very well-known guy in string theory. And so he criticized our implementation, saying you don't do it for this or that. Of course, we know that. And we know that it's not easy to do. And ours is the first step of a couple of papers written by other theorists where that case is covered. Now, there are always cases which need to be studied and extended.
All right. Since there are no other questions, let me invite Somshaptak De for the next talk, which is jet substructure methods for polarization measurements of boosted hadronic W bosons. So you have 15 minutes.
Okay, firstly, I'd like to thank the organizers for giving me the opportunity to present this work. Okay, so today I'm going to talk about how to measure the boosted hadronic polarization of boosted hadronic W boson using jet substructure observable or jet substructure method. This work has been done in collaboration with Professor Vikram Rentala of IIT Bombay and Professor William Shefford of Sam Houston State University. This is the first version of the work on which we did some major upgradation, and today I'm going to talk about those upgradations. Okay, so this is the main outline. So let me start by giving the introduction. Okay, so at high energies, longitudinal gauge boson scattering would violate unitarity in the absence of Higgs boson, or if the coupling of the Higgs boson with the gauge boson is not the same as that predicted in the standard model. In either of the cases, this scattering amplitude will grow as energy squared and the unitarity will be violated. Now, to solve this issue, if one introduces a Higgs boson with the same gauge coupling G, then it will result in a diagram like this, whose scattering amplitude will grow as energy squared with a negative sign. So this will cancel its effect and the unitarity will get restored. Now, there have been many BSM theories as well, which states that there may be some massive Higgs boson present or maybe some massive technohadrons present, which predominantly decays to longitudinally polarized W boson at high energies and may be responsible for the restoration of unitarity. So it's very much important to look into the vector boson scattering at high energies, specifically longitudinal vector boson scattering at high energies, and hence it's important to measure the polarization. Now, this is what a vector boson scattering looks like in LHC, where W plus and or W minus, this W boson can either decay leptonically or hadronically. Currently, CMS and Atlas has measured the W polarization in its leptonic channel. But we know that the branching ratio of the W decaying to hadrons is about 68%. So if we were to measure the polarization fraction in the hadronic channel, it would increase our statistical graphs over the polarization fraction. And also, we don't have to think about the neutrinos and the missing energy. We can reconstruct the full kinematics of the final state particle. Henceforth, we look into the hadronic channel of the W boson, rather hadronic decay of the W boson, and try to estimate the polarization of the W boson. Okay, let's look into the parton level angular distribution of the W decay product first. Let's say W plus is decaying to U and D bar in its W rest frame. And this angular distribution will solely depend upon theta star or cos theta star. Now, using helicity conservation principle, we can establish relationship between this decay amplitude and cos theta star for both the polarization state of W boson. And from the distribution here, we could see that the angular distribution for longitudinally polarized W boson is maximum when cos theta star is 0, which indicates the fact that the decay products prefers to align themselves perpendicular to the boost axis. And for transversely polarized W boson, the distribution is maximum when cos theta star is either 1 or -1, which indicates the fact that the decay products prefer to align themselves either parallel or antiparallel to the boost axis. Now, from this, we can see that cos theta star is a good polarization discriminator for W boson at its rest frame. Now, what we need is a lab frame observable, which can give us a direct inference on this rest frame distribution. So we move on to how to construct a lab frame observable. So first, let me tell you the distribution of the W decay rate as a function of its decay polar angle, which is given by this equation, where the transversely polarized W boson will follow a distribution like 1 plus cos squared theta, and longitudinal will follow 1 minus cos squared theta. This is normalized as 3/4. This is normalized as 3/2. And these are the polarization fraction, which are constrained by this equation, that is Ft plus Fl should be equal to 1. Now, if we had access to the experimental distribution of the W decay at different theta star, then we could fit the distribution to this equation and extract out the Ft and Fl. But we don't have right now. So, okay, so these are all parton level things. Now, at LHC, what we see are all hadron level things. So at hadron level, for a highly energetic W boson, the two jets that are coming out from the W decay, which corresponds to two quarks at parton level, will be highly collimated and will combine to form one single jet, which is called the fat jet, and that would correspond to the W boson. and the two quark jet will be the subject of that fat jet. Now, how to construct this theta star from this final state particle in order to measure the polarization? Well, one way, that is the way that CMS has tried to do, is to construct the opening angle between two subjects. And this opening angle is related to theta star through this equation. So, but we see that this opening angle is a poor proxy variable. This is the behavior of opening angle as a function of cos theta star. And we could see that this opening angle has very flat values for large values of cos theta star, and it is even flatter for high boost. So for a high energetic W boson, if one measures the opening angle and makes some errors, then the error will propagate and will give a large error in the inference of cos theta star. So what we do is we suggest another alternative proxy variable for cos theta star, which is delta E. So if we boost the W rest frame to the lab frame, we get a configuration like this, and we say that the energy difference between these two quarks will be a potential polarization discriminator at the lab frame. And this is how we relate the lab frame observable to the rest frame observable. So if you like, from the expected distribution of the from the expected distribution, we can conclude, or rather we can infer, that for longitudinally polarized W boson, there will be equal distribution of energy between the two quarks, and there will be unequal energy distribution between two quarks for transverse modes. So how to construct this angular distribution, which we call P theta? So first we identify the W fat jet, then we use n subjectness to identify the two subjects inside that fat jet and reconstruct the energy difference between those two subjects. And we also note down the momentum of W fat jet. So upon getting the reconstructed energy difference and the momentum of the W in the W lab frame, we take the ratio and construct this proxy variable P theta. So once we have event by event measurement of P theta, we can make the distribution, fit it to the W decay rate, and extract out the polarization fraction. Okay, so let me show you the performance of a proxy variable, but first we need to construct templates, like templates of how P theta is for purely transversely polarized W boson and purely longitudinally polarized W boson. So we do a theoretical simulation of this process where PP going to a fictitious particle, where fictitious particle decays to W plus and W minus, and they decays hadronically. This is the flowchart we have followed to construct those two templates. So we have kept the mass of the fictitious particle to 100 GeV, and we have considered this phi to be scalar when we are generating longitudinal templates, and phi to be pseudoscalar when we are constructing transverse templates. And since we are talking about boosted W boson, we have kept the PT of W between 800 to 1000 GeV. We did showering, standardization, and gen clustering in FastJet. And note, we didn't do any detector simulation, and we imposed these two criteria to tag the W jet, and then we construct the P theta. Okay, to demonstrate the efficacy of a proxy variable, we have constructed the cos theta distribution in various bins along with the P theta distribution for both the templates. And we can see that the P theta is a good proxy variable for cos theta star less than 0.9 with some spread, which is kind of expected due to subjet misreconstruction or non-perturbative effect. But in the last bin, which is from 0.9 to 1, the proxy variable is not a good one for cos theta star. So the plausible explanation is that for cos theta star greater than 0.9, at leading order, at parton level, W decay will be in such a manner that one parton will lie along the boost axis and another parton will lie against the boost axis. And if we go from the rest frame to the lab frame, the parton that lies opposite to the boost axis will change into a soft wide angle emission that will get removed by jet grooming. That will result in a single prong jet. Now there is a non-zero probability that there could be radiation coming out from that single prong, and it would behave as a double prong jet and would satisfy the cut criteria. So that's why, okay, so the angle between those two prongs will be determined by QCD, not by the partonic level distribution. And henceforth, we get a flat distribution like this in the last beam. So hence we can say that P theta is a good proxy variable for cos theta till 0.9. Okay. So finally, we get a 1D template of P theta. This one is for purely longitudinally polarized W boson, and this one is blue one is for purely transversely polarized W boson. We also did simulation for the QCD background. And in principle, if all these three distributions were characteristically different, then we could do a fit and extract out the polarization fraction. But from this figure, we could see that the QCD background distribution is quite similar to that of the transverse distribution. And we found out that this closeness is due to the value of insubjectness cut that we choose. So what we did is, instead of applying both the insubjectness cut and the mass cut, we just applied the mass cut and constructed the distribution between P theta and tau 2,1, which is the insubjectness. Okay. So yeah. So this template, so we can fit this template in this expression to extract out this FL, FT, and FB. So what we did finally is we applied these 2D templates to extract out the polarization fraction in a VVS scattering at HLLHC. So we did a crude estimation of the number of events expected at HLLHC. We take a current CMS study on VVS, and this is done at 138 femtobarn inverse, and we scaled up to 3000 femtobarn inverse or 3 attobarn inverse, and also we looked into 10 attobarn inverse of data, and these are the events that we found out. And also we have assumed 20% of the signal events to be longitudinally polarized. So longitudinal W is 425 and transverse W is 1739 events for 3 attobarn inverse events, and for 10 attobarn inverse of events, these are the values. Okay, so what we did is we constructed pseudo data by taking the linear combination of these three templates in this ratio, and then adding a Poissonian noise to construct the pseudo data. Pseudo data is fitted in this linear combination of the templates to extract out these three parameters by minimizing the chi-square. Now, alternatively, what we did is we switch these parameters to N total, which is the summation of NL, NT, NB, FL, which is the ratio of NL by N total, and FT, which is the ratio of NT by N total. And we did this procedure for 10,000 pseudo data and noted down the average reconstructed values and compared with the truth values. This is for 3 attobarn inverse luminosity. This is for 10 attobarn inverse luminosity. And finally, we found out that, okay, so we can detect the transversely polarized W boson with 30% accuracy at 3 attobarn inverse and 20% accuracy at 10 attobarn inverse. But we cannot detect the longitudinal polarized W boson, as they cannot be distinguished from 0. So what we feel is that if longitudinal W boson polarization is enhanced in a BSM scenario, then this technique could be useful. Otherwise, it helps to measure the W boson polarization in VBS at HLLHC to within a 20% error. And these are the summary. That is, we have proposed a new technique which uses J substructure method to construct a proxy variable P theta, which does a better job than the current proxy variable that CMS uses. And yes, this is the result. Yes. Yes, also. So that's why we aren't sure, like, how p theta is doing. Means since we have very low statistics, so we are not sure. Means, but we tried to give a plausible explanation why it's happening, but yeah.
Any other question? Yes.
So initially we for this 1D template, we use these two things, mask tagging and in-subjectness tagging.
Only these two. So
These
if
two.
you include something else, then you expect that this will improve, or from the, let's say,
Okay,
the
so-
QCD background.
Okay, right. So let's say, let me show you this 2D template. Now, in CMS, they impose cut in subjectness at 0.43. So if we impose a cut at 0.43, you see that the QCD template will behave like a transverse template. Okay, but if we impose a cut at 0.43, and if we impose a cut at 0.3, then it will behave like a longitudinal template. So we refrain from using in subjectness cut and any other cuts. And also in CMS, they only use two cuts, this mask cut and subjectness cut.
So standard way of doing it is to see same sign left on pairs.
Yes, yes.
So is this method better?
We tried to motivate that we should look for hadronic channel because that have much more statistics.
But the background is always
Background
much
is
more,
also
so
right. So that's the
unless we
trade-off
do
have.
this signal to background ratio, etc., maybe
Yeah,
it will not sell so much.
yeah, right.
But this will add.
Sure. Provided we can, because the rate is so small
Mhm.
for vector Poisson scattering, the QCD. Sure, but still the amount of multi-jet background is always very, very large, extremely large. So in certain corners of phase space, there will be still events from QCD multi-jet which will satisfy similar topology. That is the main problem. Yeah. Anyway, so nice.
CMS.
So it's WW.
So you said, so if it's WW and there are two neutrinos, then how do you, like here it mattered the angle between the W decay products. So in that case, what technique does CMS use to, yeah, if both are left, you miss both the neutrinos, so you don't have this information of the W decay completely, right? And that carries some information over there. You can do some information is still there. Okay, thanks.
In measurements with leptons are always set.
So if there are no other questions, let us thank the speaker. And I understand the next speaker is not there, so
So next speaker could not come, so we'll break now. And tomorrow we had poster viewing session that we will have now because lunch will not be ready. So please, there are 7 or 8 very nice poster. We'll go there where near where we had coffee. And after that at 1,